Okay, perfect. Thank you for the introduction. Thank you for having me today here. I'm going to talk about physics-constrained autoencoders for fluid flow prediction that preserve stability. This is joint work with Michael Mühlebach and Michael Mahoney. Let me start first. So what is machine learning? We all know this, right? Machine learning or supervised machine learning aims to map a set of inputs to a set of targets. And normally we can learn a candidate model by formulating an empirical risk minimization problem. So in general, this model best fits our data, but this becomes a problem if we use highly expressive models such as neural networks. So what do? Normally we introduce some bias in form of a regularization term to have a better trade-off between bias and variance. And those regularizers we usually use are in many cases not very meaningful, at least not physically meaningful, though they're difficult to interpret. So my view of physics-constrained learning is that we want to learn a model that preserves some physical properties by incorporating a physically meaningful prior, which constrains a regularized problem. And this model is maybe not the best fit for the data, but it hopefully allows us that the model generalizes better or kind of incorporates some better interpretability. And I think this is important in scientific applications. So classically in computer vision application, we try to interpolate just our data. And there it is, not necessary that I incorporate some additional knowledge about the data because what I want to learn is encoded in the data. In scientific application, quite often the problem is I have much less data and the model may or may not learn implicitly some insights about the underlying physics. And also the other thing is in scientific application often we want to extrapolate. And this is of course a hard task, and I don't say that we solve this here today, but that's the whole hope of physics-constrained learning, that it might provide us with a framework which allows us to extrapolate better in the future. Okay, let me start with my problem setup. Well, Nathan gave a great introduction this morning, actually laid out the mathematical framework. So here again, so I'm interested in a dynamical system, which can modeled here as shown as in equation 1. So this curly A is a function which involves a state x in time. And my ether is an error term which accounts for some model errors. So as Nathan said this morning, normally we do not have access to the state, but we have some observables. So a function g of x, and we gives us a high-dimensional observation y. And that is what we have in a data-driven learning framework. And again, so we have some measurement errors we have to account for. Okay. So now given a sequence of observations, what we try to do, or what we want to learn, is a map from yt to yt plus 1. And we use here an autoencoder structure, and the intuition behind this is that the decoder is basically an approximation for this g. The encoder learns, or should be an approximation for the inverse of g. And this, what I call dynamics, this omega should be an approximation for my curly A. So basically, this architecture, without doing anything, works pretty good for a lot of problems. If I tune the architecture in the right way, it learns implicitly for simple problems, actually, some about the underlying physics. But for more challenging problems, as I will show later, this is not optimal. Okay, so if I train in a physics agnostic way, well, basically I formulate a loss function, minimizing, for instance, the mean squared error. And here, well, what I should say is that we want to learn the dynamics. So I have to enforce that the encoder is also an inverse of the decoder. Otherwise, the whole network would just learn the dynamics. But we want to analyze later the dynamics. So this is why I have this regularization term here, which basically enforces that the encoder is an inverse of the decoder, which why do we want to do this becomes clear in a moment. So now during inference time, well, we want to predict not only one snapshot, but we want to predict several snapshots into the future. And basically, we do this by composing the learned model, or kind of has this function iterate here. So the output of the first model is the input then, is the input for the next prediction, and so on. So we want to go k times into the future. We kind of compose our model k times. And now if we have this assumption that the encoder is an approximation for G inverse, or well, an inverse for the decoder, then basically 4 reduces down to 5. And now we see kind of, well, we hope that our dynamics are encoded here in omega. And now we can, well, do some stability analysis, right? I mean, if omega is linear, let's start with that. So later we might want to have it nonlinear. But if it's linear, well, I can use Lyapunov's method or for stability analysis. In a nutshell, I will talk a little bit more about it. Well, if my eigenvalue is within the unit circle, so the system is stable. If they're outside of the unit circle, the dynamical system is diverging. Well, here again, I mean, I think probably here at this audience, I don't have to talk much about it. This is probably pretty 101 dynamical system. So I'm a statistician. For me, that's new. But basically, yeah, if we have a trajectory which starts arbitrarily close to the origin, so in a ball of radius delta, then the system is stable if it remains for all time close in a ball of radius epsilon. And again, if what I just said, if the dynamics are linear, well, we can just check this by doing an eigenvalue analysis. Okay, so let me show you 2 models where we have a linear dynamics omega, and I compute the complex eigenvalues. So they're kind of trained in 2 different ways. So the one has here on the left-hand side, I use no weight decay. On the right side, I just use the right amount of weight decay. And here's the results for flow past cylinder. This is my input, my initial condition, and I use the model to predict 10 time steps into the future. This model, which has no weight decay, well, we get kind of, yeah, whatever here, I don't know, nothing really interpretable. But if the model is well tuned, so if it preserves stability, we get a pretty good prediction. I don't know exactly what the error is, but pretty low. Okay, but that is maybe not a very elegant way. So fiddle around with weight decay until the model becomes stable. Yeah, that's not what we want to do. The problem is, well, we have heard it today, right? I mean, neural networks are great. So basically, everything, or more general, we want to have something so that everything becomes auto-differentiable. I cannot it's hard task to compute the derivative of complex eigenvalues or eigenvectors. So that is the challenge here. But fortunately, we can use again ideas from 120 years ago. We can use Lyapunov's second method, which stated the dynamical system is stable if for any symmetric positive definite matrix Q there exists a symmetric positive definite matrix P that satisfies this Lyapunov equation here. And that's great. So P is symmetric, so that means we can differentiate the eigenvalues and eigenvectors for a symmetric matrix. So basically, we just have to recast our problem in this. And, well, oops, let me see. So, so our problem is now, so that we assume the underlying problem is stable. We impose in our model that the symmetric matrix P defined here by 9 is positive definite as well by incorporating a prior. It's a little bit hard to compute P, and I'm not going into the details here, so the paper discusses this, but that's the general idea. Okay, so basically our physics-informed layer has, physics-informed autoencoder has this additional penalty term here, which kind of is a stability-promoting prior, which takes the following form here. This might look not very intuitive, and I just have 5 minutes, so let me be quick. It's actually interesting to look to the Lyapunov equation in a little bit more detail, and we could assume that omega is diagonalizable and Q is chosen appropriately. So this whole thing reduces to a system of linear equations, which I have plotted here. So omega is the eigenvalue of big omega, and small p an eigenvalue of p. And then I see, well, if the eigenvalues of p are larger than 1, then the magnitude of the eigenvalues of omega are smaller than 1. And if p is, tends to minus infinity, the eigenvalues converge towards magnitude of 1, the eigenvalues of omega converges towards 1 from the right. And critical is if the eigenvalues of omega are well, converging towards 0 from the left, because then the eigenvalues of omega diverge. So that's why we came up with this penalty here. We tried other penalties like a hinge loss or so, which really do not work good, but there might be other forms. So that's actually an interesting problem to study. Okay, so let me show you quickly. Oops, that was a bit too quick. Okay, animation doesn't run. 2 examples, the flow past cylinder. I probably you're all aware with this. And another problem are daily sea surface temperature data of the Gulf of Mexico for a period of 6 years, shown here. So that's the performance. Well, I put in also a ReLU network just to show ReLU is not always the best choice. It might give us the best point prediction for 1 time snap, but if you want to go several times that, it does not perform that good. It has a large variance. And this guy here would be, in blue line is the physics agnostic model, which does not have the penalty that we preserve the inverse of the encoder decoder. Green is our model where we preserve the inverse, and red is our physics aware autoencoder, which has the additional stability prior. And that's basically what we would accept for a simple problem like the flow past cylinder, right? I mean, there's it's periodic, it should run forever. Couple of other examples here I will run quickly. It's just what happens if I change the learning rate or change the weight decay rate of the model. Yeah, so we see kind of the performance varies a little bit, but in general it seems to be good to have the additional penalty. These are data for the sea surface temperature. So example 3 is interesting. I just pick it out. So here we just go 5 time steps. Without the stability promoting prior, well, we get more or less nothing interpretable, I guess. And here, having the stability promoting prior, it seems like we get a better prediction accuracy. And again, I go here just 60 steps. I mean, you see, it's a hard problem. The error blows up. Well, we cannot look too far into the future, but going 5-6 days, I think is already good. And you see the difference of the eigenvalues of the dynamics, stable, unstable. Well, you have a couple more minutes. So one slide here, what is important, and I'm great that the speaker before me said they use small neural networks. I think it's really important that in science we should start with building a very simple model. So from a statistical, my statistical training was always kind of start with a parsimonious model, and then you can add complexity to it. But what we often see now is that people start with a very expressive model, and it works because we have nothing we can compare to it. So I think it's really good to start with a very simple model, add a little bit complexity to it. And shallow learning is good for scientific problems where we have less label data. I don't say the volume might be very large, so 10 to the minus 6 or so, where in computer vision problem, normally we work with tiny image patches, but we have millions of those patches, so I have a lot of label data. So we should not always use those techniques or those networks they use, but develop specific techniques for scientific applications. So there might be a good trade-off using more shallow networks. Summary I skip, I guess. Basically, next steps are extending our framework to nonlinear dynamics, incorporating an ODE block or some nonlinear layers. Okay, here's the corresponding paper. Questions later, I guess.